Okay, guys, welcome back. Wake up. We're going back live. And again, if you could just type in to the chat box so I know you can hear me and see my screen. Great. Okay, so Levi took a somewhat different tact to this than I did, a bit more theoretical. But now we're going to actually start to apply this in a number of cases. Okay, and we're going to extend a little bit past what Levi was talking about, in that we're going to go through a couple of other kinds of examples as well. Okay, first thing I want to do is I want to open up one of these Word files. Let me see. Okay, I'm going to start with this one. This is actually session 2. These are exercise set 2 rather than 1, but I want to start with this first one to start working. The mean SAT scores for a population of first-year Hunter students is 620. So that's for the entire first-year class of students. The mean SAT score on entry is for English or whatever it is 620. The standard deviation of scores in this population is known to be 95. We know both the mean and we know the standard deviation for the population. An investigator believes that the mean SAT score first-year psychology students is significantly different than the mean score of the population. He's not speculating if it's greater or less than, just that it's different, right? The mean of he takes a random sample of 36 psychology majors, and he finds that the mean for the random sample of 36 psychology majors is 648. So what do we have here? We have all students is one population, and their mean is known to be 620. And a second population is psychology students, and their mean is estimated to be 648 based on a sample. So we have a known mean, and we have one group that's sampled. So this is our classic single sample t-test. Now, as Levi had mentioned in the lecture, and as we started to allude to before, the first thing we want to do is we want to test this claim by setting up a null and an alternative hypothesis, right? So what's our null hypothesis? Our null hypothesis is going to be, well, our null hypothesis always starts off with an equality, right? So we're going to say that the mean for all Hunter students is equal to the mean for psych students, right? And then we're going to want an alternative hypothesis. And our alternative hypothesis is, as he wants us to prove, that they're different. So mu for all does not equal the mu for psychology students. Notice that this is not directional. It's either they're equal or they're not equal. We're not predicting ahead of time whether the psychology students have higher confidence intervals or, higher mean SAT score or lower SAT score. Okay, in fact, most likely in practice, you might actually say to yourself, well, by launching this study, I'm really kind of setting up this null and alternative hypothesis because I didn't know before I started it whether or not they would be the same or equal. So this is a single sample t-test. So I am going to be comparing the two means to one another. So the first thing I want to calculate is that standard error that I'm going to need in order to calculate the t-score. Okay, so I'm going to calculate my standard error. Okay, so my standard error is equal to the standard deviation divided by the square root of the sample size. Sample size is 36. Now, what's my standard deviation? Well, I know my standard deviation. Did they mention it here? They don't give us the standard deviation of the sample. They give us the known standard deviation of the population. So we're going to assume that the population and this sample have the same standard deviation. In other words, we're going to assume that we know sigma. So in this case, I'm going to say we know sigma. So the standard error is going to be equal to, where is it up here? It's 95 divided by the square root of about 36 or 6. It's going to be divided by 6. right? So that's going to be equal to, well, let me go over to Excel and calculate it here. I'll get a little bit fresh area over here. So it's equal to 95 divided by 6. So our standard error is equal to 15.883. Okay, so now we're going to calculate, we're going to do a t-test, a single sample t-test. We're going to do it by hand rather than using SPSS. We don't have the data imported into SPSS, so it's going to be kind of incumbent on us to be able to do it this way in this particular example. So I'm going to calculate. Now, let's think about this a second. Should I be calculating Z or should I be calculating T? Anybody got an opinion on that? Am I working with Z or T?
Z.
Yeah, why am I working with Z? It is Z. Great. We know our standard deviation of the population. We know sigma, so we know our standard error precisely, right? So we can actually calculate the Z-score. So what's the critical to be 95% certain, or to be less than 5% chance of being wrong? In other words, an alpha error of 5%. What does my Z-score, my critical Z-score, have to be? Yeah, 95%. What is the Z-score that represents 95%?
1.96.
Right, it's equal to 1.96. So we need a Z-score bigger than 1.96 in order to be able to say that these two means are far enough apart for us to say that they're different. So let's calculate Z. Z is equal, oops, that's an X. Z is equal to the, what is it, was 648 minus the mean for all students, 620, divided by the standard error, which is 15.83. Okay, let's see what we get when I do that with Excel. Equals 648. Or actually, I know it's 28, so I'll just put 28 in there on top. Divided by 15.83. Okay, and I get a Z-score of 1.76. So what's my conclusion with regard to my null hypothesis and my alternative hypothesis?
It is
Not enough, not big enough, right? Alpha error is going to be more than 5%. So what do I say? What do I say in that situation? I fail to reject. Hypothesis. Oh, did I forget something there? Oh, no, I didn't. I'm okay. Yes. There, good. Okay, everybody agree with that? Vicky, the 36, I took the square root of 36 and I used 6 there, right? It's square root of 36. Okay, does everybody agree with me? Anybody uncomfortable with what we just did here so far? I'm going to hold out until I get a couple of answers.
I want you to repeat the first part when you said state the null and alternative hypothesis.
Yeah, we're going to be doing it about 3 or 4 times. You'll see it's going to happen again. Okay, good. We seem to be okay. There's a little bit of a lag, so it takes a little while for me to get your responses.
Then you said Y and YZ.
The reason why we use Z instead of T is because we knew the population, the standard deviation of the population is known to be 95. And that's what I used for the standard deviation. Right? Since I know sigma, since I know the population standard deviation, I can go ahead and use the Z-score. If I didn't, I would have had to calculate my standard deviation from my sample of 36 students. Then I would have to use the T-score instead. Use the T-score when you're basing your standard deviation on the sample instead of the entire population. Almost always in real life, we'll wind up using the Z-score, T-score, because we're working with samples for the most part. Okay, so let me see what I can do next here. Okay, this is a very similar one. Okay, let's do this one. I'm not going to do that. That's kind of the same. Okay. Let's see if we know. That one's known also. I want one that's not known. Oh, how about this one? No, I'm looking for one that's a little bit different. I'll come back to that one. I'm going to take one of these and change it a little bit. That way I can demonstrate what I'm trying to demonstrate. Let's see. Okay, that'll do. Bored with that one. I want this one. Okay, I'm going to use this one right here. The mean of close friends for the population of people living in New York is 5.7. That's known. Maybe some study that included everybody or something like that. And let's say I don't know this about standard deviation of the population. I'm going to take that out. Okay. So an investigator predicts that the mean number of close friends for introverts will be, I'm going to say, for the starters, I'm going to say different. You're going to see why I'm changing this in a moment. Different than the mean of the population. The mean number of close friends for a sample of 26 introverts who were surveyed is 6.5. Okay, now I don't like that. I don't like these numbers. Let's make that 4.5. Make it lower. Okay. The mean for close friends for a sample of 26 introverts is 4.5. Okay, does this support his prediction? Level, alpha is equal to 0.05. What's our null and alternative hypothesis? Well, our null and alternative hypothesis are H null. Trust me on this, I'm getting there. Okay, my null hypothesis is that the mean number of friends for the general population is equal to, for all, is equal to the mean number of friends for introverts. That's my null hypothesis. My alternative hypothesis is that they're different, that the mean number of friends for all people in New York City is different than the mean, different, not equal to, the mean for introverts. Okay, so now in order to do this, I need to do a t-test. In order to do a t-test, I have to calculate a standard error, standard number, standard deviations, apart that these two means are equal to. Well, the people who have the average New Yorker, the whole population, has a mean of 5.7. The sample of 26 introverts has a mean of 4.5. And undo. 4.5, and I want to add this in, and the standard deviation of the sample group is 1.3. Not the standard deviation of population, but only of those 26 people in the sample. So now I don't know sigma anymore, right? All I know is the standard deviation of the sample is equal to 1.3. So when I calculate my standard error, I can't say sigma over, the square root of the sample size, right? Right now, instead, I'm going to use the standard deviation of the population of the sample divided by the square root of the sample size to calculate sigma, which now means I have to calculate the t-score, not the z-score. Okay, so let's calculate what that is. My standard error is going to be equal to, let's see, standard deviation is 1.3 divided by the square root of 26. Okay, I'm going to use Excel to do this. Okay, and it's going to be equal to 1.3, divided by the square root of 26. And calculate that. It comes out to be 0.25. 0.25. I'm just going to round that to 0.25. Okay, so my standard error is equal to 0.25. Okay, so now I calculate my t-score, my number of standard errors apart, which my two means are. So in other words, x bar, the mean for the sample, minus mu for all, minus mu for all, divided by the standard error. Okay, let's see what that comes up with. Okay, so the difference between my value for my sample, which is 4.5, and the value for all people in New York is 5.7. Okay, so that's equal to 4.5 minus 5.7 divided by my standard error, which is equal to 0.25. Okay, so what is that going to be? Let's see what that is. Is equal to 4.5 minus 5.7 is minus 1.2. The sign's going to be irrelevant, by the way. Minus 1.2 divided by my standard error, which is 0.25. Okay, so what's my t-score? My t is equal to, what was it again? 4.8. Negative 4.8, positive 4.8, doesn't matter. Negative 4.8. Okay, so what is my critical value of t? First of all, number one, t came out to be a very large number. So my inclination is to think that this is really a significant difference. But let's check it. Now, how do I know what my critical value of t is? Oops. What is t critical? Okay, well, we got to go to our t table, right? Okay, where'd it go? Here it is. Here's our t table. Okay, so negative 4.8 is our t value. Well, now to find my t value, I want 5% alpha, 5% chance of being wrong. That's the same thing as a 95% confidence interval, right? 2.5% each tail. Okay, so I am going to go down this column, right, to the critical value that's represented for a sample size of, and what was the sample size again? 26, right? Sample size is 26, so it's 25 degrees of freedom. So my t-score, my critical value of t, is 2.06. So I'm going to go back over here. I'm going to note that my critical value of t is 2.06. So now I have exceeded my critical value of t, right? What about my p-value? Is my p-value, or significance, same thing as significance as SPSS uses it, is my p-value or significance less than 0.05? What would you guys say to that? Remember, as the t-value goes up, the p-value goes down. So is it less than 0.05? I got a yes over here. How about you guys online? Do you agree with that? Yes, we use n minus 1. Okay, you guys agree with that? That it's less than 0.05? Yeah. So if my p-value is less than my acceptable level of error, which is alpha, right? In other words, if my critical value has been exceeded, then I can reject my null hypothesis and accept the alternative hypothesis. Okay. So we've proved, what have we done? We've proved that there's a difference in the mean, at least to the level of 5% chance of being wrong. We have demonstrated that there's a difference between these two groups. Okay, so now, remember this word here used to be lower than the mean of the population, right? Okay, well, that's important because that suggests that I'm assuming that it will be significantly lower. I'm only going to go one direction, right? So the investigator predicts that it's going to be lower, right? So my null hypothesis is that they're the same or greater than. Mu all is the same or greater than mu for introverts, equal to or greater than. And that leaves as my alternative hypothesis that mu all is greater than, I should have made this less than mu all, that the introverts have, I had it right the first time, that the introverts have fewer or equal number of friends than the rest of the population. Okay, mu all is equal to or greater than mu for introverts. And my alternative hypothesis is that I'm sorry, I should have done this the other way around. I'm sorry to confuse you on this. Okay, my null hypothesis is that really the best way to do this is to start with your alternative hypothesis. What are you trying to prove? You're trying to prove that introverts have a lower mean number of friends than non-introverts. In other words, that they're less than, that introverts have fewer friends than the rest of the population. So our null hypothesis has to represent the other possibility, which is equal to or greater than the rest of the population. So this is the way you would set this up. Anybody know what you call this kind of hypothesis? Okay, remember before when we use hypothesis, says mu all equals mu one equals mu two, and mu one doesn't equal mu two. We call that a two-sided hypothesis. Could go either way, but in this case, it only works one way. We're making the assumption that the only way that this is the only possible outcome here is that either they're the same, or that the introverts have fewer friends. This is a one-sided hypothesis. When you have a one-sided hypothesis like this, right? Well, if you look at the t-table, let me see if I can't get it to come up. When you look at the t-table, okay, and we went down to number 25 down here, 25, to go across, okay, we used the 95% confidence interval, the number for 95% confidence interval, to set our location, our column, for where we're going to look up our critical value. And that's based on the fact that the probability in each tail, the probability that the value is so extreme that you would only likely see it in less than 5% of its chances, means that there's only 2.5% of its being that much bigger, or 2.5% of its being that much smaller, right? So we would use this column because 95% confidence interval two-sided is really 2.5% on each end. Well, instead of that, when we do a single-sided test, we're predicting it can only be either larger or smaller than the other value, not both. So we only need to get that 5% in one tail. So we would use the column for the 90% confidence interval instead. So our critical value of t for a single-sided test like that would be 1.7 instead of 2.6, 2.06, right? We get the same outcome. We're still going to reject the null hypothesis. But notice that our threshold for being able to reject the null hypothesis is so much lower than it is for a two-sided test, right? Because we're only giving it the possibility of being wrong in one direction rather than either direction. So the takeaway there, the lesson there is that a one-sided test is less rigorous than a two-sided test. It's easier to reject the null hypothesis when you use a one-sided null and alternative hypothesis. Very frequently, you really can't predict ahead of time that the answer could only be one direction or the other direction, right? You might be able, maybe if you're testing a drug and you know the drug is a vasodilator, it dilates blood vessels, you might say to yourself, well, the only thing, and you're doing a blood pressure survey, you might say to yourself, this drug can only decrease blood pressure because of the way it works biologically. It can't increase it. So we want to see whether it's the same or it really decreases it significantly, right? So that might be a situation where you get a one-sided test. But for the most part, you don't see that situation too much. For the most part, you stick with a two-sided test simply because it's more rigorous, a more rigorous statistical test, and also because you don't have to justify your reasoning to use a one-sided test, which would be less rigorous. Okay, so usually we're going to stick to two-sided tests. But if you happen to see it, if it comes up, you know what we're talking about in terms of a one-sided test. Okay, so now there's a couple of other complications here. Okay, and to show you those complications now, I'm going to go to that other Word document, or maybe to those, maybe instead of that, maybe I'll open up open recent. I think it's that one. Okay. Oh, before we do that, before we do that, I do want to do one other different kind of example. Okay, suppose we want to know the true proportion of Irish Americans who approve of a wider representation of groups in St. Patrick's Day parade. In 2000, the committee asked a random sample of Irish Americans if they approved of wider representation of all groups in the parade. Out of 1,381 respondents, 496 said that they approved. Well, what can we say about that proportion? Okay, well, what we can say about that proportion is, let's see, let me get my pen here so I can write down some of these numbers so I don't have to remember them. Oops. So we had N is equal to 1,381, and the number that approved was 496. Okay, so now our sample size is quite large, nice large sample. So we can actually calculate the proportion of people that approved wider participation was 496 over 1381. These numbers are made up, by the way. Okay, and what is that anyway? Let's calculate it. That's equal to 496 out of 1,381. Okay, so the proportion that approved was 36%. Okay, so our P cap, the percentage of the population of this sample that approved, was 38%, 0.38. Okay, what we're really interested in is what P is. P is the proportion of all people that are marching in the parade. Maybe there are 50,000 people marching in the parade. So this is a relatively small sample out of 50,000 people that might be marching in the parade, but we really want to know the proportion for all of those people. Well, we randomly sampled 1,381 people, so we don't know P. We probably will never know what P is, but we do know what our proportion of our sample is, what our p-value of our sample is. We can use that to actually calculate a confidence interval for the true proportion. Okay, so this is what I'm starting with. That's my sample proportion. In order to calculate a confidence interval, right, I have to, number one, I have to decide whether I'm using Z or T, right? Well, when we work with proportions, we're generally working with very large samples. So this is a very large sample. And I'm going to say to myself, since it's a very large sample, I'm going to say we have enough confidence to work with Z rather than worry about the sample size. If you look at the T-table, you'll also notice, well, it goes up to 100 or 200 anyway, right? So it would be hard to use it for that big a sample anyway, without assuming that you're going to use the same value as Z anyway. So for 95% confidence interval, we're going to be talking about z equal to 1.96. Okay, so let's develop a confidence interval for this. Okay, so p cap, right, plus or minus the margin of error. What's our margin of error going to be? It's going to be 1.96 times our standard error. How do we calculate standard error for proportions? Well, anybody remember? The square root of p times 1 minus p over n. Okay, so for our specific problem here, it's the square root of 0.38 times 0.62 over 1381. Okay, well, let's calculate what that is. Let me get to Excel here. Okay, here we go. That's going to be equal to the square root of 0.38 divided by 0.62, times 0.62, divided by 1381. Okay, it's going to clean out those parentheses first, so it should do it in the right order, and the answer comes up to be 0.01. So now our p cap, which is 0.38, our 95% confidence interval is going to be 0.38 plus or minus 1.96 times 0.13. 0.013. Okay, so let's calculate this margin of error. This margin of error now is going to be equal to 1.96 times the standard error. It's going to be equal to 0.026. So margin of error is 0.026. 0.38 plus or minus 0.026. So let's see what we wind up with there. 0.38 equals 0.38 minus 0.026. And it's going to be equal to 0.38 plus our margin of error. So our 95% good, yes, Vicky. The 95% confidence interval is between 0.35 and 0.41, right? Roughly. We rounded off a little bit here and there. Okay, so it's going to be between these two numbers. So one of the things I might ask you is, well, does it appear? Are you 95% certain it's that if you asked all of the members, everybody participating in the parade that particular year, are you 95% certain that they would reject the idea of wider participation? Well, 50% is outside of this range, right? So yeah, you would say, well, it's definitely different than 50% because it's definitely lower than 50%, the true proportion, which we don't know, but we're estimating based on this confidence interval, because 50% is not within this range. Okay, so we could use the confidence interval that way. Another way we could use the confidence interval is if I told you that we had another population, right? In other words, these are people that participated in the St. Patrick's Day parade, and P cap was 0.38. But then a year later, we ran this test again, and we asked them again, and this time we got 0.42, maybe 0.44, let's say. Maybe a little bit off, 0.44. Let's leave it at 0.44. Okay. Now assume that for a moment that the standard error was the same in both cases. There's other ways you might handle that, but assume for a moment the standard error was in both cases. If I wanted to do a t-test here, the way I would do a t-test is I would say my null hypothesis is that the proportion for let's say it was 1970, and this 1970, proportion for 1970 is equal to the proportion that we're willing to accept a wider participation in 1980. Okay, now let's say our alternative hypothesis that the proportion for 1970 is not equal to the proportion for 1980. Okay, well, let's see what's going to happen here now. Okay, so that's my null and my alternative hypothesis. Okay, so let's calculate what our z value is for the difference between these two proportions. We don't know p, but we know p cap for each one of those years. So we're going to say p cap for 1 year, which is 0.44 minus 0.38. How many standard errors are part of those? Well, I got to divide by the standard error, and the standard error was equal to 0.025. Okay, well, let's see what the z-score is there. The z-score, not t-score, but z-score, since it's a very large sample and it's a proportion, is equal to 0.6 divided by 0.25. So what's our z-score there? Let's get, let's go back to our, I was in there already. Okay, so our z-score is equal to 2.4. What's my critical value of z for rejecting the null hypothesis? For 95%, or alpha is equal to 0.05. It's 1.96 again, right? So I can reject my null hypothesis that they're the same and accept my alternative hypothesis they're different. I could actually go into the Z's table, the standard normal distribution table, and calculate what my p-value would be in this case, right? Like, so for instance, I could look this up and it's going to be equal to, I'm going to make this a negative because it's going to work easier to find an area with on a negative. So I'm going to make this a minus. Whoops. All right, just so I get a negative number there. So I'm going to say equals norm S dist, parentheses, give it the z-score, it'll give me an area at the end at the corner of the curve, and it's equal to 0.008. That's the area under the left side of the curve that's left when you look how far apart these two are. So it's 0.008. Since I'm doing a two-sided test, I want both sides of the curve, so I double this. I know I'm confusing you a little bit when I say that, but hang in there. And double that. Oops, click in there. Yep. So the probability of being wrong is my significance, or my p-value, probability of being wrong if I reject the null hypothesis, is 0.016, is less than 5%. So because my z-score is z-critical, because my p-value is less than 0.05, I can reject the null hypothesis. Yeah, I know I confused you a little bit with that part. That's okay. Don't hang on there. We're gonna, this week and going into Monday, we're gonna play with this a little bit, and probably you won't be forced to work with it in this manner. And the reason for that is I'm going to show you the way that for the rest of your life that you'll probably really be doing this. Okay, so now let's look at all the different possibilities that we have here. Let's look at all the different possibilities that we have here. The other possibilities that we have here, make sure you play this end part of it, because, okay, good. The other possibilities that we have here is that we could be using, instead of a single sample and compare it to a known value, instead of a proportion, right, we could be working with two samples, a random sample of people taken this year and a random sample taken next year, a random sample of people taken from this part of the country, random sample of people taken from this part of the country, and we need to combine the two of those. So when we do that, we're going to wind up with a mean X bar for group 1. We're going to wind up with a standard deviation for group 1. And then for the other group, we're going to wind up with a mean for group 2. And we're going to wind up with a standard deviation for group 2 as well. Two different standard deviations. Not only have two means, we're going to have two standard deviations. How are we going to deal with that? Well, what we're going to do is we're going to say to us, if the standard deviation I got from group 1 and the standard deviation I got from group 2, if they're close to one another, I'm going to pool those numbers together. And even though I got two different means, I'm going to use all the numbers together to calculate my standard deviation, a single standard deviation, so I can do my t-test. If, on the other hand, if they look like they're quite different, like one is double the other, for instance, is enough to say it's quite different, then I don't want to pull them. I have to do a more complicated calculation for this because I don't have a single standard deviation that I can use to measure the difference in standard errors across these two. Okay, so I'm going to go right now. I'm going to go to some samples that I have up here. I'm not sure that these are on Blackboard. They might be on Blackboard from last week's class. I think that's likely. Okay, so we already saw a single sample. Now I'm going to look at this two sample t-test. Now here's a two sample t-test where I'm comparing measurements for males, measurements for females, and let's see what the averages are. Equals average, parentheses. Okay, that's the average I got for the males, and I'm going to drag this across, and that's the average I got for the females. It looks different. How about standard deviations? Okay, here's what the standard deviation looks for males, and here's what the standard deviation looks like for females. Okay, and I'm going to look at those and see what I get. Well, you know, they're not double. One's not double the other. They're not exactly the same, but it's not so much that it double the other. So I might be inclined to combine these two and get a single standard deviation. I'm doing this a little bit different than real life, but just to give you an example of why I might be interested in doing this so that I can use a weighted average of these standard deviations instead of having to worry about the fact that there's two of them. So now if I want to calculate my t-score, it's just this minus this divided by the standard, I'm sorry, I would then calculate a standard error. And my standard error was going to be calculated, since I pooled these, I put these two together, my standard error is going to be equal to, going to be my standard deviation my weighted standard deviation divided by the square root of the sample size. What's the sample size? Well, actually, I'm going to use, it's 16. But when I work with degrees of freedom, I'm going to use that. I'm going to use 16 to I don't know why it gave me an error. Don't worry about the error. My standard deviation, my standard error is going to be calculated based on the full sample size. But when I go to my t-score and I look up my critical value at t, and I want to know what the degrees of freedom are, it's going to be n group the size of group 1 plus the size of group 2 minus 2. In other words, it's the sample size of this one minus 1 added to the sample size of this one minus 1, since I'm pooling these two. Okay, so now let's take a look at this in real life. I am going to do this calculation, not manually, but I'm going to be doing it using SPSS. So I have an SPSS version of this file right here. So let me open SPSS. Okay, and I'm going to say open. Oops. Open. Data. And I'm going to go up to the top. And two sample t-test. Okay, and here we go. And you may notice that I've substituted, because of the way that SPSS organizes data, I've substituted the numbers 1 and 2 for male and female. In fact, okay, that's a variable view, data view. Whoops. There we go. You can actually get SPSS to show it to you that way as well. So now I'm going to say to myself, let's run our t-test. I'm going to say analyze. I'm going to say compare means, except this time instead of a one sample t-test, yes, you can use SPSS for most of these tests. I mean, maybe on the homework I might give you a problem where I ask you to calculate a t-score and whether you're going to reject the null hypothesis using Excel or using your calculator. But I probably would give you a simple version, like a single sample test, rather than ask you to do it by hand for a more complicated test. So I'm going to click on Independent Samples t-test. Okay, and what's the test variable? The test variable is the values, those numbers that we're finding the means of. And the grouping variable, that's going to be the two groups that I'm looking at. I have to define them. One represents female and two represents male. You got to make sure you get the numbers right too. If it was 0 and 1, it's going to mess up. Okay, I'm going to click OK. We'll find out if it's going to mess up right now. Okay, options. You want to make sure it says if for a 5% alpha is equal to 5%, 5% chance of being wrong. You want to make sure it says 95% confidence interval in there. If you want 99, if you want a 1% chance of being wrong, alpha equals 0.01, you might want to change that to 99% confidence interval. So I'm going to click OK. The output window is going to come up, and let's see what it gives us. Okay, first thing it does is it calculates the means and the standard deviations. They should look familiar to you because we just calculated those. And then it calculates for each one of them a standard error. Okay, it calculated this one based on sample size of 9, took that number divided by the square root of 3, and gave you a standard error for that, and a standard error for that one. Okay, so now let's see what SPSS decided to do in terms of whether it wanted to consider the standard deviations equal variances, or unequal variances. Okay, well, in fact, it actually, it's a computer, so it has the capability of doing both. Notice that when it does the independent samples t-test, when we did the single sample t-test, it was a single line, the result. Now there are two lines. One line is if you assume equal variances and you pool them together. The other line is if you you don't assume equal variances because they're so different. Now, SPSS is going to help you out in choosing which one of those two lines to use. Okay, we decided to use the top line because one standard deviation was not double the other one, right? Let's see if SPSS agrees with us. This box over here, this 4x4 box right here, where it's titled Levine's Test for the Equality of Variances. There's a statistics score, it's 1.456. Don't worry about that particular number. But next to it is a significance or a p-value, just like we use with the other tests. And the deal here is that just like everything else, we start off with the assumption that the variances are equal, unless we can prove that they're different. So our assumption is that the variances are equal. Now, if our significance, our p-value, is less than 0.05, we reject the idea that they're equal, and we use the lower line that the variances are not equal. Okay, so we're not assuming that they're equal. So in this case, my significance is 0.245. I would be wrong 24% of the time if I rejected the idea that they're equal. So I'm going to stick with that. So it's not less than 5% chance. So I'm going to stick with that top line. That's exactly what we did ourselves. So what does a t-score come out being? T-score comes out to be 2.184. How many degrees of freedom is it? Okay, the degrees of freedom is equal to 16. 9 and 9, 18 minus 2 is 16. That's where it got that. Now, what's the critical value of t? Well, I'll go and look it up. For 16 degrees of freedom, a double-sided test, 95, 16 degrees of freedom, the critical value of t is 2.12. So if I exceed 2.12, I can reject my null hypothesis. I've exceeded the critical value. Well, it's 2.18. I can reject my null hypothesis. Now let's check it to significance. Also, I should get the same result if I look at the significance. And the significance, or p-value, the probability of being wrong if you reject the null hypothesis, the probability of you getting an outcome like this if these two were really from the same population, is less than 0.05. It's 0.04. So that's more evidence. So the critical value of t is exceeded, which tells us we can reject our null hypothesis. And the significance tells us the exact probability of being wrong if we do that. And since it's only 4%, less than 5%, that's confirmation that we can reject our null hypothesis. Okay, you guys comfortable with that? Makes sense? Okay, now let's drop the next shoe. Let's go and open up another bit of data. Okay, and I'm almost done here. I just want to get to this one. Let's go and take a look at this one over here, which surprisingly is called two-sample t-test unequal variances. Okay, so now let's calculate this one out. The mean of this group, average, parentheses, of these guys here, oops, almost missed that one, is 10. I think it's the same. Average, parentheses, of this group is that much, similar to what we had before. But now let's calculate two standard deviations. Okay. Okay, and this one is going to be equal to standard deviation. Okay, and it turns out to be, oh, look at this. They're very different. One's almost 3 times the other. So maybe I can assume equal variances for these two groups. Well, let's try it in SPSS. Okay, let me get SPSS up. So I'm going to open a new file. That file, I'm going to import that or open it in SPSS. Two-sample unequal variances. I kind of planted these data. You can obviously see I planted these data sets to be like this. Okay. Okay, so now I'm going to repeat my test now with this new data. Analyze, descriptive statistics, compare means, independent samples t-tests, and I'm going to put the values into the test variable, put gender into this grouping variable. I'm going to define the groups again, 1 and 2. I'm going to say OK, and I'm going to ask it to go ahead and calculate this for me. Okay, well this time, see how the output window looks? This time, here's our means are the same. Here's our standard deviations as we just calculate them, except this time we can see there's a big difference between the two of them. So let's look at our test for the equality of variances. Well, this time the significance here comes out to be less than 0.05. So I can reject the idea they're equal variances and use the bottom line. In fact, there's really not much of a difference between the two of them. Okay, but let's take a look at what we get. So our t-score now is 2.511. Our number of degrees of freedom is a very odd number. And next week I'll show you where this number for degrees of freedom comes from for, when I show you the formulas that you would use to calculate the t-test manually. Okay, matter of fact, tonight I'll post it onto the same stuff as we have here, but we'll go over that on Monday night. So at any rate, so that my t-test is 2.51, 10 degrees of freedom, fewer degrees of freedom. So my critical value of t is going to be a bigger number, but despite that being a bigger number, right? What's my significance? What's my probability of being wrong if I reject my null hypothesis? I'm not going to bother looking this up on the t-table. I'm just going to go straight here. So I got a result here for my probability that I would get this extreme of value if they were from the same population, and it's 0.03. So you guys tell me, do I reject my null hypothesis that the two means of the two groups are the same, or do I fail to reject my null hypothesis that the means of the two groups are the same? With a result of 0.31 for my p-value or significance, should I reject my null hypothesis or not? Reject. Correct. Thank you very much. Right? So I think we're starting to get a handle on how we use this t-test, but imagine what we've learned now. What we've learned now is that if we're working with a numerical variable, blood pressure, we want to compare the blood pressure of one group to another group. If we want to compare the blood pressure of a group of people that are on a placebo to one that's on a drug, if we want to compare the number of emergency room visits by people that have asthma versus people that don't have asthma, or smoke or don't smoke, any numerical variable now, we have a tool for comparing two groups and being able to say that we're going to start with the assumption that the two groups are the same. That means that the two groups are the same. But by the time we're done, we're going to be able to say with a known level of certainty that I can reject the idea that they're the same and say that they're different. And I can say this drug works, or I can say this intervention works, or I can say that People who smoke have more emergency room visits, right? And so on and so forth. So this is an enormously powerful tool for working with numerical variables. After we get done with this, we're going to look at, we're going to continue with this a little bit more going forward, but then we're also going to look at what kind of tools we have for comparing categorical variables, things like diabetes or not diabetes, right? Or things like whether ethnicity has some impact on some other similar variable, whether a person has diabetes or not. Both categorical variables. Diabetes, yes or no, and ethnicity is a nominal or a named variable also. You can work with those together using other tools. And then later on, we'll take a look at using two numerical variables. Does increasing your sugar intake in grams per day have an effect on your glycol tolerance test, which is both of those are numbers, and see if there's an association between those two numbers. So for right now, we now have our first real good solid tool for analyzing data that we might actually collect and work with. Okay, so we ran pretty late tonight, and we covered a lot of material. We learned a lot of stuff tonight, and I think we're in a good shape. I think for this semester at this stage. So at any rate, I'm going to post homework number 4, which is going to involve some simple stuff with the t-test. You'll have some time to work on it, though. I'll make it due past the holiday. And as far as Monday is concerned, I'll be posting links to the attend online. So don't come. I mean, if yeah, I only had one other person in here tonight. Don't decide to come on all of a sudden this coming Monday, since we're going to be doing it strictly online. Okay, and as I said, if they screw up this Blackboard thing, and not even just if there's a problem with the Blackboard update or the outage for most of the day, because they're supposedly not going to be back on until literally our class start time. I think 5 or 5:30 or something like that. So I don't want to depend on that. So I am going to be emailing you links and materials, or posting them somewhere where you can get to them without having to get to the Hunter Blackboard. So that way I know that we can go. I would say let's ditch the class and have a nice 4-day weekend, but we really need to be able to keep up with this stuff because summer session is just so short. We really can't afford to miss too much. So have a good night, guys. I hope I didn't scare you too much with this stuff, or Levi and I working together kind of, didn't scare you too much with this stuff. But I think we have a pretty good handle on it in the long term. So good night, guys. Bye.